if there are any, you don't have to by any means, but I like to make sure that I give a chance, for you guys to ask about that kind of stuff before we get going too far. Grudes? 14? Okay. Oh, let me paste in the problems. That would be easier. So this one is a graph, or referencing a graph. So I'm just going to kind of do it on the sheet here. So it says, state whether the labeled point is a max, a min, or a neither. So here we have a local max. That's a relative high point. Here we have a local minimum. That's a relative low point. Good with that. And this 0, comma, negative 0.22 is a neither. So that's neither increasing nor decreasing, so we don't have to worry about that one. It was labeled there as a distractor for you. Then in my intervals, I see an uphill section here, and then a downhill section here, and then an uphill section there. Agreed? Okay, so my increasing interval will be from negative infinity to negative 3, along with 2 to positive infinity. Again, remember when we're naming these intervals, we're using only the x coordinates. And my decreasing interval will go from negative 3 to 2. Now, you might want to, some might argue that at this single point, it's flattening out, and maybe it's not decreasing. If you think back to your actual definition of decreasing, if I pick a point, if I include that point and pick a point immediately after it, it's going to work. You're going to have like a negative slope. If I pick a point immediately before it, you're going to have a negative slope. So it is part of it. Yes. Of course. No problem. I can't remember if it was this section or another section. Somebody asked me about that point. I don't remember. I essentially teach this class 6 times. Like all of my sections are either the honors or traditional for this class. So it's just like we're using the same problem sets. We're using the same textbook. I can't keep anything straight about who asked me when. I'm going to apologize about this all year long. Because it's just a blur. You know what I mean? Or the same thing over and over again. It's like, when did that happen? I'm not sure. Elizabeth, are you happy? Yes. Okay. Raylan? 18? Sure. So 15, 16, 17, and 18 are just calculator questions. So we'll just run through that on my calculator. I'm not going to really write anything down because this is a question you do like entirely on your calculator. So I'll start off by going to the y equals menu and then typing this function in. So x times, and then to get the absolute value, if you remember back from last year, you have to press the math button, which is right here below the green alpha button. You have to go over to the number tab, and it's the first command in the list there, ABS is short for absolute value. And then I'll do 2x minus 1. And then hit graph. Nope. I guess I should have Zoom standard. I was messing around in another class, I think, before this. So there's my picture. At first glance, I don't see any maximum or minima, right? You guys agree? Now, it's possible that maybe like right in here where the graph looks to go flat near the x-axis, that maybe there is a little like doop or something in there and I just can't see it. It makes me suspicious in a question that's asking for maxes and mins to get a function that doesn't have any maxes and mins. That seems a little odd, right? You would think, as students in your experience. So what I'm going to do is I'm going to zoom into that area just to double check. There's probably nothing there, but there could be. And the fact that it's asking me for max and mins, I would want to make sure. Does that make sense to you guys? So I'm just going to go maybe from -1 to +1. And then I'll change my scale to be tenths instead of ones. And then -1 to +1 and change that scale also. Now you could just use the built-in zoom in function, and that would be appropriate as well. I like to pick my own windows because I tend to think I'm smarter than the calculator's automatic zooming or whatever, but you know, the window doesn't so much matter as just being able to get a reasonable picture. Which, aha, there it is. It was hiding on us. Okay, so now we'd use the max and min functions to find these, right? I have one local maximum here and one local minimum here. So second trace, I'll do the maximum first. So first asks me for a left bound, so anywhere over here is okay. That's where my cursor's at already, so I'll just press enter. Right bound would be somewhere over here, so I'll just move my cursor over there. That looks good. Press enter. Guess doesn't matter. So that looks like 0.25 and then comma 0.13. And then I need this guy's a minimum. So let's second trace, choose a minimum, move over. I gotta be somewhere over here, so I just moved over a little bit. Press enter. And then my right bound should be over here somewhere. So over there, press enter, and that should be good. And I got 0.5. Notice here, this number ends in E -6. What does that capital E -6 mean on your calculator when you see stuff like that? Yeah, that's scientific notation. So this is times 10 to the -6. So it's 0.0000133 yada yada yada. If I round that to 2 decimal places like it's asked for, I get 0. And in all reality, my suspicion is that is actually 0, and it's the approximation algorithm that the calculator is doing, like cut off with just a little tiny scrap left before it finally like zeroed all the way out. And that's really supposed to be 0. If you get a number that small, that would be my suspicion. How could you check that? If it's actually supposed to be 0 or if it's actually supposed to have a little residual there? You could try plugging 0.5 into your function and seeing if it gives you 0. It will. Raylan, does that feel good? You're welcome. Don't put it past me to give you something where you have to, the initial graph appears to have nothing and then you might have to zoom in a little. That won't be the last time that happens. At least in the honors course, right? Hold on. I need to look at my Margot.
Can you please do 21?
Sure. Okay. So this one, with what we're given and what we know about odd and even functions, I can't tell initially from looking at it, well, I mean, I can, but we can't tell initially by looking at this whether it's going to be odd or even or neither. So we're just going to have to go into this blind. You could also graph it and take a look at the picture and just see, like, what kind of symmetry does this look like? That's reasonable to do also. But we'll just start off by evaluating g of -x. So that gives me 1 over -x. And that's the same thing as just a negative sign and then 1 over x, right? The negative doesn't matter where it's at in the fraction. You can put in the top or the bottom or out front. But the takeaway is that's -g of x. So since we have g of negative x equals negative g of x, we're odd. No problem, my dude. Grace. Sure. So that's 21, 22. Again, this one we can look at and tell, right? We have an odd degree monomial and another odd degree monomial, so this should be odd as well. Okay? But let's prove it. That's not a proof, right? That's just us knowing what we're supposed to be getting. So we'll start by doing k of negative x. And I'll input negative x in for x. If I have a negative to the third power, that gives me a negative. And a negative times a negative is a positive. So far, so good. Now, I observe here that this is not the same thing as what I started with. The signs are flipped, right? So it's not even right away. Cool? I mean, we knew that already, but... So what I'm going to do is check to see if it's odd. To do that, I'm going to now factor a negative sign off. So when I do that, everything flips. And if I look now, that part is g of x, or I'm sorry, k of x, and I still have that negative sign out front. So I have negative k of x, which is what I need to be odd. Is that okay?
Yeah. So like, do I have to show all that since we can tell by looking at it?
So since it says support your answer algebraically, yes, you would. If I just asked to determine whether the function is odd, even, or neither, looking at the graph would be appropriate. But if it says prove, or it says support your answer algebraically, you need to do a little bit more. Is that okay?
Yeah.
But always, like, the first thing I would do is just, do I know what the answer is supposed to be on a problem like this? And then can I make the algebra match? You know what I mean? Like, support what I already know. Because again, this is one where you can look at it and know instantly. Well, virtually instantly. You can know without having to do anything, right? What you're supposed to be getting. Which is nice, right? Remove as much ambiguity as we can. Elizabeth, you have got another one?
Yeah. Quick question. How do you get the absolute value?
On your calculator?
Yeah.
So you press the math button, and then you go over to the number tab, the NUM, and it's the first option that says ABS. You're welcome. Natalia, or is it Natalia or Natalia? Natalia, I'm sorry. I should know this.
Can you do one more?
Sure. So I think 20 should be neither. Yeah, definitely. So let's do that one. Oh. So again, we'll start the same way by doing h of negative x. So negative of negative x squared is just going to still be negative x squared. And then negative x minus 1. So far, so good? So if I compare this to the original, that's not the same, so I know it's not even. Good with that? I'll continue on. So now I'm going to factor out a negative sign. And if I compare this to the original, it's also not the same. So I know that this is not negative h of x. So I know it's not odd. So I conclude then it's neither. You're welcome. How are we feeling? Bit better? Anybody else with questions on things? Raylan? A negative outside of the parentheses?
Yeah.
Okay. So you saw in the answers, right, that it looked like whatever. Oh, sorry. Or something like this, right? This is just supposed to be like a dash.
Oh,
Like I could have put a semicolon there just as easily. Yeah, no, totally fair question, because like looking at this and not knowing what I was thinking, like that's like what, why is that there? It's just like a dash. It's not, or a semicolon. It's not supposed to be the negative sign. So perfectly reasonable question, like totally weird of me to have chosen a dash there instead of a colon or whatever. These are things that like you write it yourself and you're like, oh yeah, that's fine. And then somebody says it and you go back and you look at it and you're like, why did I choose to do that? I don't know. But this is, yeah. So the answer is there's never one there. Caitlin. Elizabeth, sorry. Is that your sister?
yeah.
I every time I'm sitting there like gonna call you Caitlin, I'm like, nope, her name's Elizabeth. Why am I calling her Caitlin? And it just kind of dawned on me. Okay, anyways, go ahead.
So is -2, is that the local, that's the local max, right?
Yes. Correct. Okay, so if this was the overall highest point of all the high points, then it's global. Because the graph has an arrow pointing up, it can't have a global max. But if you had something like this, that's a global maximum. If the graph did this, then it's just local. You get it? Okay. Yeah, no problem.
Wait, so the lower the global.
Again, if you have an overall lowest point, 3, -2 can't be global because the graph also points down. Right? So if you had something like this, that's a global min. But if it did this, it can't. It's now just local because it's not the lowest point. Yeah, no problem. Okay. We feel good about the homework. Again, can always come back and ask more about questions later. Anybody else, though, before we move on? All right. If you would clear your... Okay. So today, we're going to talk about section 1.6, which is all about asymptotes, and then start section 1.7. I don't know that we'll finish it. That's a meaty bite right there, but that's okay. So section 1.6 is about an asymptote. So we've talked about asymptotes last year in our Algebra 2 class. An asymptote is just like an imaginary line on a graph that the graph approaches but doesn't cross. We've talked about asymptotes that can be horizontal, vertical, or even diagonal or oblique. Did you guys, that's all familiar, right? Okay. So let's just look at a quick example. Let's say we have x squared plus 3x minus 3 over x squared plus 2x minus 3. Oops, so we should probably say this is f of x equals. So let's just generate a graph for this real quick. Again, I'm going to use a graphing software to do this. That's going to be a little bit neater than me trying to draw by hand, and it'll give me a bigger picture than I can get from the calculator, so I can actually write on it and make some comments and whatnot. So just FYI, that's what I'm doing right here for just a second while I get it ready. If you're interested, this is a free program, though, that I'm using called Graphmatica. If you Google that, they have a free version that you can download and use. It works quite well from your computer. If you're ever like, oh no, I don't have my graphing calculator, but I have my computer, what can I do? Well, Graphmatica does like it's pretty easy to use, and it can actually graph things that your calculator can't easily graph pretty easily. So if you have a function that's like written, where like you have x plus y equals 7 or something, you can just type it in like that, and the Graphmatica can handle it. You don't have to do any rearranging, and it can graph things that aren't functions even, which your calculator would struggle to do without being a little bit clever about it. But this is the graph of what what I just typed in there. So I see a vertical asymptote here at what looks like -3. And I have a vertical asymptote here at +1. Do you remember how we find the vertical asymptotes for a rational function like that? From last year? You just set the reduced denominator equal to 0 and solve. So in this case, if I look at the numerator does not factor. So I don't have to worry about that, but factoring the denominator, two things that multiply to give me -3 and add to give me +2. And if I set those pieces then equal to 0 and solve, there's my asymptotes, right? At -3 and at +1. Does that ring a bell from last year? It should. It should. Okay. If you look closely, you might also notice that we have almost a horizontal asymptote, right? Why do I say it's almost a horizontal asymptote? Yes, Jackson.
It's like the middle line crosses it.
Yeah, because the graph does cross it in one location. Technically speaking, we would call this an end behavior rather than an asymptote. But for right now in this section, we're going to use those terms like interchangeably. Everybody's okay with that? So even though this is crossing in like one place in the middle because the ends are still, the end of the graph is still behaving like an asymptote, we're going to call it an asymptote. For this section anyways, we'll differentiate a little bit later. Are we okay? I just want to be real clear about that this is not really an asymptote, but we're just going to let that go for right now and not worry about that little detail, because in terms of what we're trying to accomplish in this section doesn't really make that much of a difference. So finding the vertical asymptotes are relatively easy. Finding the horizontal asymptote can be quite a bit more challenging if you remember back from your Algebra 2 class last year. For these rational functions, there's like all these different cases for when you'll get like a horizontal or a slant asymptote or whatever. Do you guys kind of remember that? Maybe you don't. But there's like a whole, like there's like 3 different cases, and like it depends on this and this, and you have to compare things, and then it'll tell you which case you're in, and then you actually have to find the asymptote, and it's kind of a hassle. Another way to think about this is we can do this using our graphing calculator to get an idea of what's going on. So let's just type in our function into our graphing calculator. Oh, actually, I'm going to do it this way. So if I press alpha and y equals, that gives me the shortcut to the fractions menu. And this first fraction option will give me just a, like the normal looking fraction, numerator over denominator. And then I can type it in without having to use any parentheses, which is maybe a little bit easier. The only downside to this is that when you type it in this way, it's going to give you a fraction back, even in your like XY table or whatever. But that's not too big of a deal. So there's that. I just typed it in. Everybody's okay? Again, if you were in my class, we talked about that fraction shortcut a whole bunch of times, so you should be familiar with it. I'm sure Miss Morgan mentioned, and if she didn't, it's alpha and y equals is the shortcut to the fractions menu. In case you want to use that later, it's quite helpful, and it allows you to type the thing in just like it looks on your piece of paper without having to worry about a bunch of parentheses. Okay, so what I want to do is I want to use my calculator to kind of confirm this asymptotic behavior, that as the x's are getting bigger and bigger and bigger, the y's getting closer and closer and closer to a single value. In this case, it looks like that value is about 1. Everybody's okay with that notion? So what I'm going to do is I'm just going to graph this on a big window, so maybe like negative 1,000 to positive 1,000 on my x's. And then I'll just reset my y's back to negative 10 to positive 10, just whatever the standard was there. And I'm going to hit graph. Oh my goodness. That is not what it's supposed to be doing. Is it? No, I didn't even see any asymptotes in there. What is going on? Why is it giving me this? Oh, so it is giving me some things. Did I type something in wrong? What was that? Plus 2 minus 3. Why is it not showing? Anyways, whatever. I don't care. It doesn't matter. I have the right thing in here. So what I'm going to do, oh, I know why I can't see it. It's because it's so wide. Whatever. I got the right thing in. It's fine. What I'm going to do is I'm going to press second and trace. And I'm going to go to the value option. And I'm just going to see as I get progressively bigger x's, I'm just going to confirm that we're getting progressively closer to, in this case, 1. So 10, oh no. All right, I lied. I'm coming back and I'm changing this. I'm just going to use the fraction. I'm going to use I'm going to use parentheses. I don't want this fractions in here. It's just going to make life harder. I'm sorry. I was like, oh, why would I type this in not using this option? Then I'm looking at the values I'm getting. I want this to be decimals. It'll be just much easier to look at. I'm sorry. You know, sometimes it doesn't matter and sometimes it does. And this is a case where, like, I think it kind of matters. Well, it's going to make my life easier if I can look at the decimals. Okay, so second, trace, value. I'm going to pick 10 to start with. And I'm, 1.0 whatever, right? And then I'll do second and trace and maybe pick 100 next. And I'm getting closer to 1, right? 1.0098, yada, yada, yada. And then I'll pick, say, value and maybe do 1,000 now. So I'm just going up by a magnitude of 10. And there I get 1.03 zeros, yada, yada, yada. So you see as I'm getting, my x is getting bigger and bigger and bigger, my y is getting closer and closer and closer to 1. That's my evidence for, at least at this end, the asymptote appears to be 1. I also have to check at the negative end, though. Right? Because the asymptote is has to work on both ends. So I'll just do the same thing, except negatives. And this is something I would just, so I'm a little bit under 1. And then we'll do negative 100. So I'm getting closer to 1, still underneath it. That's good. And then the last one, say negative 1,000. And I'm getting real darn close, still underneath though. So again, all I'm doing here is just kind of numerically confirming that I'm getting that asymptotic behavior at the ends, right? So if we're asking you to like verify numerically that the horizontal asymptote is, what the horizontal asymptote is, all you do is include the table of values, like, 10, 100, 1,000, and then the y value you got for each of them, and show that it's getting close to 1 in this case. Is that okay? Let's do one more example. So I'll go back into the y equals. I'm going to clear this out. And this time, let's do 3x divided by x plus 1. I'm not going to bother to change the window because the only thing about this value command that I've been using is the point that I'm looking for has to be in the viewing window. Like I can't do value x equals 10,000 because I haven't graphed the point 10,000, right? Because my window only went up to 1,000. So that's one thing to keep in mind. If you get an error doing the value, it means that you're picking an x that's outside of your window range. Calculator's like, I didn't compute that point. What are you doing? Anyways, so here's my graph. I'm going to do the same thing. I'm going to look at x equals 10, 100, and 1,000, and then negative 10, negative 100, and negative 1,000. And just to confirm they're all approaching the same value, which I can see pretty easily from my graph is the case, right? What did we do back in the day when I was in high school and we didn't have a graphing calculator? We did the same thing just manually, like you plugged in 10 into your calculator, you got the number. You plugged 100 in, got the number. You plugged 1,000 in and got the number. This is just less typing to do it this way. You know what I mean? But it's the same thing. So when I plug 10 in, I get like 2.7 and change. When I plug 100 in, I get 297 and change. And when I plug 1,000 in, I get 299 and change. So I'm pretty convinced that we're heading towards 3. Got to check the negative end though also. So negative 10, I get 3.33 and change, negative 100. I get 303 and change, getting closer. And when I do, negative 1,000, I get 3.003 and change, and that's, again, confirming what I saw on the other end. Is that okay? That's all I want to do, all I want to talk about with regard to asymptotes. Not much to say there. Just, we know what they look like. We've talked about how to find the vertical ones in this case, and now we've talked about how to kind of confirm a horizontal one. Natalia? Of course. Okay. 1.7. This is a big section. We have a lot of topics to talk about in here. So if we don't finish today, we'll just kind of pick up where we left off next week. Because I think, what do we have, like 25 minutes or something? I don't think I can finish this all in 25 minutes and not without just like bulldozing through it, which I don't really want to have to do. So we have the 4 basic operations. So let's define those. So let's say let f and g be 2 functions with intersecting domains. Then, for all, actually, let's say that. Let's use that symbol. So there's a mathematical symbol that's like an abbreviation for the words for all, and it's the upside down capital A. I'm going to use that symbol here. You're not required to use that symbol. I just figured we're in an honors class with a bunch of kids that potentially are interested in doing some mathematics in college. That's a symbol you might end up seeing. Why not just introduce it now? It's pretty common. So the upside down A just means for all. So we'd say then for all x's in the domain, we should probably say, let's be specific, in the intersection of the domains of f and g, the algebraic operations performed on f and g are defined by the following. Okay, so this starts with f and g being 2 functions with intersecting domains. What do we mean by intersecting domain? Well, it means that they have to have some x's in common that are defined in both functions, right? So for example, I couldn't add these two functions together, right? F would be defined for all the x's that are greater than or equal to 2. And G would be defined for all the x's that are, oh my goodness. Let me, that's wrong. Sorry. And G would be defined for all the x's that are less than or equal to 1. So there's no x's that are defined for both of them, right? So there's no, you couldn't combine these in any way. You couldn't add them or subtract them or multiply them or divide them, because any x you plug into that works for one is undefined for the other. You know what I'm saying? So we're just saying that, like, by intersecting domains, we're only talking about, okay, if we add these two things together, whatever value for x we're using has to work for both of them already. That's all we're saying. Does that make sense? You know, like the graph for G looks like this, and the graph for, or I'm sorry, the graph for F is the one on the right, and the graph for G is the one on the left. Oops. Oh, it's here, but there's no points in common between them, right? No x values in common. That's what we're saying. So there has to be some kind of x's in common. Then using those x's that are in common, this is how we can add, subtract, multiply, or divide them. So if I have the function f plus g evaluated at x, how do I do that? Well, I just evaluate f at x and g at x and then add them together. If I have the function f minus g evaluated at x, how do I do that? Well, I evaluate f at x and subtract it from g at x. If I have the product f times g evaluated at x, how do I do that? Well, I do f of x times g of x. And lastly, if I have the quotient, f divided by g evaluated at x is f of x divided by g of x, provided that g of x is non-zero. Why does g of x need to be non-zero? It's the denominator of a fraction. So again, hopefully none of these definitions are surprising, right? This actually makes adding, subtracting, multiplying, and dividing functions really quite easy, because instead of having to worry about, like, what does the sum of those two functions really mean, and create a new function, if you know what f is and you know what g is, you can figure out what f plus g is by just doing each of them separate. You know, doing f of x and then g of x and adding them together. Okay. So let's say that, let's do a specific numeric example here. So let's say f of x is 2x minus 3, and g of x is the square root of x plus 2. And let's just do a couple of function operations here. So if I want to do f plus g of x, I know that's the same as f of x plus g of x. So that's 2x minus 3 plus the square root of x plus 2. Just substituting things in, right? Can I do any simplifying between 2x minus 3 plus the square root of x plus 2? Any combining of like terms, anything like that that I can do? What do you guys think? That's a big negatory. Nothing we can do there to simplify that. Again, I can't take things that are outside of a square root and add them with things underneath a square root. And obviously the x's and the constants are not like terms and can't be combined. So let's do g minus f of x next. So again, following our definition, that's the same thing as g of x minus f of x. So that's going to be x plus 2 minus the quantity, 2x minus 3. Remember, if f of x is what we're subtracting, that subtraction has to apply to all the terms in f of x. That's why I put the parenthesis there, because the first thing I'm going to do is distribute that negative through. So certainly I can do that simplification. Is there anything else I can do though? Nope. That's as far as we can go on that one. Any questions so far? Relatively straightforward, right? So let's say we have g times g of x. Well, that's g of x times g of x. So what was g of x? That was the square root of x plus 2 times the square root of x plus 2. Can I simplify that anymore? Well, that would be the square root of x plus 2 squared, right? Can I simplify that anymore? What would I get? X plus 2. Everybody think that's the end, or that's correct? Why am I putting an absolute value around it? If I take a number and I've taken the square root of it, what kind of number do I have to be getting? If I've taken the square root of it, it has to be a positive number. If I square it, that positive number also has to be positive, right? So.
I have a question. Like, how does the square just go like both?
Because, sure. So the square and the square root cancel out.
Oh, okay.
Right, because they are inverse operations. Does that?
Yeah.
Okay. No problem. Again, though, I wouldn't mark it wrong if you neglected to put in the absolute value there. So it's not a big deal. But I want to point out that anytime you like square and then square root right after, you're getting the absolute value. In fact, I think that was one of the 3 ways we defined an absolute value way back in Algebra 1 or 2, depending on where you did it, was that it was equal to the, like x squared square rooted. Anyways, that's immaterial. Let's keep on going. So the quotient of f and g evaluated at x is f of x over g of x. So f of x was 2x minus 3, and g of x was the square root of x plus 2. What do you guys think? That's okay? Would anybody do anything else? John? Yeah, so typically we don't like to leave a radical in the denominator. And I'd be good with leaving it that way. If you wanted to distribute the square root of x plus 2 to each of those terms, that would be okay also. I wouldn't personally because it's just like more writing. And to be honest with you, I wouldn't even mark this wrong if you didn't rationalize the denominator, although at this level we should be doing that kind of automatically. What's weird about that rule, or that preference of rationalizing denominators, we make a big deal out of it in high school. And by the time you get to like a Calc 3 course, your professor's gonna be like, stop rationalizing the denominator, it just makes everything worse. Like it's fine. And then you quit doing it. So it's such a strange like preference that we've decided like for a while we want to do this, and then eventually it becomes more trouble than it's worth, and we're like, stop doing this. So if you plan on going and doing a lot of mathematics at some point, get ready for that to happen, because it probably will. There is a fifth operation that applies only to functions. So addition, subtraction, multiplication, and division are things that you can do on real numbers and other stuff, right? There's a fifth operation, though, that involves only functions. It's called composition. So let's define how that's done. Let f and g be two functions such that the domain of f intersects the range of G then we say that the composition of f and g, which we write f compose g of x. So this little open circle here is not the letter O. That's like a multiplication dot, but instead of it being a dot, it's like an open circle. So it's not the letter O. It's not read as fog. Please don't say fog. It makes me want to stab my eyes out. Maybe it's ears, since I'm hearing it. Makes me want to stab myself in the ear. So that's like the multiplication dot, except it's an open circle. That this is equal to f of g of x. So let's talk about this first sentence for a minute and what that really is saying. Josh? Absolutely. So it says f and g have to be two functions such that the domain of f intersects the range of g. So what that's saying is, if I pick an x, I have to compute g of x, which is an output, right? The output for g of x has to be inside of the domain of f, right? Because what am I plugging into f? G of x, right? So like, for example here, like if I pick x equals 3, and when I do g of 3, I get 10, and then I'd have to do f of g of 3, which is like f of 10. So what we're saying is that this range for g has to intersect with the domains of f, because that's what I'm plugging into f. Does that make sense as to why that's there? Again, a lot of times we would just bowl past some of this stuff in an honors class. I'm going to sit down and talk about like why we need all these extra conditions there that we just kind of ignore. But that condition is in the definition to make sure that you're not like composing two things and getting something undefined. It's just ensuring that when we do the composition, we actually get something that we can, get a defined function afterwards. Okay, so let's do a couple of numeric examples here. And this will probably be the stopping point after these. Sound good to you guys? So I have 2x squared minus 3x for f, and negative 3x plus 4 for g. So if I do f compose g of x, that's f of g of x. And g of x is negative 3x plus 4. So in place in x, I'm going to plug in negative 3x plus 4. So I'm taking the x's and plugging in that. Everybody see what we did there? Again, this was something you did last year in your Algebra 2 class, so it shouldn't be wholly unfamiliar, but if it's like, yo, it's been a minute, I don't quite remember how that worked, it's okay. That's why we're doing it again and doing the examples. What I need to do now is to simplify. When simplifying, the first thing in the order of operations is exponents. So how do I simplify negative 3x to the fourth squared? Begins with an F, then an O. Grace. Foil it out. So I'm going to do that part in my head. Is everybody okay with me just foiling this in my head? Okay, so that's 9x squared minus 24x plus 16. And then the next part I'm just going to distribute through. So plus 9x minus 12. And then I need to distribute the 2 through also. So that's 18x minus 48x plus 32 plus 9x minus 12. And then we'll combine some like terms and end up with 18x squared minus 39x plus 20. Just FYI, for those of you that want to go, whoa, how the heck did you foil that out in your head so fast? This is all it is. First thing squared. This is 2 times the product. So negative 3 times 4 times 2. And then the last one is 4 squared. That's how I'm able to do it so fast in my head, in case you're wondering. If you weren't, you're like, yo, I'm just going to do it the way that I, the textbook FOIL definition. That's cool too, no biggie. If I do g of f of x, well, or g compose f of x, that's g of f of x. F of x was 2x squared minus 3x. So when I plug that into g, I get negative 3 times 2x squared minus 3x plus 4. And the simplifying there is so much easier because all I really need to do is to distribute things through. And we're done. What observation can you make about composition after doing these two examples? In general, composition is not commutative, right? F compose G is not the same as G compose F. Order matters, unlike addition or multiplication, or if you carefully define what we mean by subtraction. Order matters here. And let's stop at this point. This seems like a good place to stop. All right. So